Hi guys, welcome back to part 3 of this connecting the graphs of rational functions to the end behavior and determining what the asymptotes are. So what we're going to do is we're going to go back, and I've already done these problems, and as you can see here, I'm just going to zoom in real quick just to remind you. We took a look at dividing out these rational functions. Notice that the denominator is linear. And so when the denominator is linear, you can basically divide the denominator into the numerator by using synthetic division. And if the degree of the denominator is exactly one more than the degree of the numerator, then we know that we have a slant asymptote. And you can see the slant asymptotes here on this one, the equation of which was y equals x plus 4. We can see the slant asymptote here. The equation was 1/2 x minus 1. And then the slant asymptote here, the equation was negative 2/3 x minus 1. Now, we started this process by you just finding the equation of the line, pretending like I gave you the function in the beginning in the picture. What we're going to do is we wanted to be able to find what the slant asymptote is without having to have a picture in front of you. And so what we did down here is we used synthetic division. So I'm just recapping from the previous video. So we did synthetic division, but remember, synthetic division is only dividing of the form x plus a, where a can be positive or negative, and that's quote unquote the zero of that linear factor in the denominator. If your factor in the denominator, like in this case right here, we were dividing by 2x plus 2. When we divide out, we set it equal to 0. We find the 0 of the denominator. So we were dividing out negative 1 down here at the bottom. When I divide that out, I have to remember that synthetic is dividing by x plus a. So, or in this case, x plus 1, because x minus negative 1 would be x plus 1. And so when you divide that out, here that what you end up taking a kind of gander at is that what you have here is not really that function h of x. And so if you divide and there's a coefficient, you have to add back in the coefficient by, I multiply both sides by 1/2 so that when you distribute here, you would get a 2x plus 2 in the bottom, and that would become h of x. And then we have our x minus 2 here, and then we have our 3x plus 1 there. Okay, so that was kind of what we did in that past video is using synthetic division. Now, coming down here, what I want to do is talk about, okay, what are we basically talking about? So number one is check if your denominators, the degree of the numerator is one more than the degree of the denominator. That's how we know that we have a rational or have a slant asymptote. If it's linear, like it is here, you can use synthetic division, and that's typically the faster one. However, if there's a coefficient, you need to remember to actually add it back in. So that's what we talked about just above. However, I did want to come in and talk about long division, because long division is useful and it actually doesn't have the limitations of synthetic. It just is a little bit longer to do. I also wanted to point out that if your denominator is nonlinear, if the degree of the numerator is one more than the denominator, you always have a slant asymptote. However, you can only use synthetic if that denominator is linear. So you do have to use long division. If you had like a cubic divided by a quadratic, you would have to use long division in order to do it. So I thought I would come back in and I would show you long division. So we're going to do that first here in this video, and I'm going to redo the example that you had above with the h of x, where you were dividing the x squared minus x plus 1 by 2x plus 2. So we're going to do that as our first thing to kind of show you how long division works. All right, so our review for long division, what you do is you basically take a look at the what you're dividing into. So we want to take this 2x, you look at the first term, and you're going to divide the 2x into the x squared. And so those are the two things that you look at initially. Now, if you need to, over on the side, when we ask how many times does 2x go into x squared, what we're basically trying to do is this division of x squared over 2x. And if you simplify that, it's going to end up being 1/2 x. And so that's what goes in up here in your quotient. So how many times does 2x go into x squared? It's going to be 1/2 x. Then what you're going to do is you're going to multiply that times both of the terms in your divisor. And so we write it below. So it's kind of like what you would have done in middle school with long division. 1/2 x times 2x would give us x squared. And then 1/2 x times 2 would give us plus x. Then what you have to remember in long division, which is different than synthetic, you then would subtract those terms that you just wrote down. And if you've done this correctly, your first one should always cancel. Go ahead and then combine your second terms together. So make sure you line them up so that you have like terms. So negative x minus x is negative 2x. Bring down any terms that you have still hanging out here. So we bring those down and then we repeat the process. Now I'm going to ask how many times does 2x go into negative 2x? It goes into it minus 1 times. Because if I was going to do negative 2x divided by 2x, I would get negative 1. And then I repeat the process. I multiply times the two terms, okay, again. And then we just write it down. So I would have minus 1, so that would be minus 2x minus 2. Then we subtract. And when we subtract, we would cancel the first two terms out. We would combine the other two together. Plus 1 plus 2 gives us a 3. And we know that we're done with our long division because the degree here is 1. When you get down to a constant, that degree is 0. When the degree is smaller, then you have a remainder. So the 3 right here is going to be my remainder, and then we've got our quotient. And so you can kind of compare this when you come back up here. Remember that 1/2 x minus 1. If we come back over here, there's that 1/2 x minus 1 right here. So that was the quotient right there. And then notice that my remainder is right there. Now, what's different about this that might be a little bit nicer with long division is notice I didn't have to correct for missing the coefficient. The long division that we did takes into account that there's a coefficient there because you don't have to divide by something of the form x plus a. Synthetic really is only a shortcut for dividing by x plus a, and then you would adjust if you didn't have a linear relationship. But again, and then what I talked about over here is that the idea of the long division works for everything. It just takes longer to do. So if I do have a linear denominator, I pretty much always use synthetic. But if it's nonlinear, if it's a cubic over a quadratic, you do have a slant asymptote, and you would go ahead and do the division, and the quotient would be the slant asymptote when you do it. All right, so I just thought I would talk about that. All right, and then just adding in the second bullet right there is me just saying the quotient, regardless of which technique that you use, the quotient is the slant asymptote. And technically, when you are doing these, if it's not the degree of the top is not just one more than the bottom, if it's two more, you start having what we call other asymptotes, which would be a parabolic asymptote if the degree is 2 more, or a cubic asymptote if the degree is 3 more, and so on and so on and so on. We just don't really talk too much about the other ones, the parabolic and cubic asymptotes and stuff, because at that point, it's not really as important. We really are looking for asymptotic lines. So when do you have horizontal? When do you have slant? Taking a look at it. All right, so I'm going to leave you to do this rest of this page on your own, and I'll pop up some questions in the Ed puzzle for you guys to do for these problems down here, just on this last page. So got to give you some feedback on how you did on those. So try those first, answer the questions in Ed puzzle, and then you guys are going to come down and do your homework, working on the worksheet that's attached at the end. And so that will wrap up this video series on connecting the equation of rational functions to their graphs, finding horizontal asymptotes, finding slant asymptotes, and knowing when you have quote unquote other asymptotes, and then using this idea of the survival of the fastest or fittest, the dominant terms at the top and the bottom, to determine what the end behavior is of the graph. Notice that I don't have to actually do the division to get the end behavior. The shortcut is the survival of the fittest. If I just want to know where the ends go, I don't actually do division. But if I want to know like the equation of the slant asymptote or the horizontal asymptotes, then you have different strategies that you're going to use for that. You only really need to use the synthetic division if it is an other asymptote, slant, parabolic, cubic, and so on. For all the horizontals, you can tell without doing the actual division. And I just want to, one last thing before I leave here, I did want to talk about kind of why this happens, like when you're doing the quote unquote limiting process. So I'm going to come back to this h of x that we had here. So when I'm doing this limit for h of x, if I was going to take, and let's just leave it in black. So I'm going to do the limit as x goes to infinity of h of x. Now, because we've already done the division and we know that h of x is the same as doing the limit as x goes to infinity of the 1/2 x minus 1 plus the 3/2x plus 2. So all of that is me just putting h of x in an equivalent form, okay? And one of the properties that we'll learn next year in calculus, and it's kind of intuitive here when you look at it, that when you have the limit of two things that are added together, I have this part right here and this part right here, you can treat them when there's addition between them as the limit of a sum is the sum of the limits, so you can look at them individually. And so we could ask the question, and it's kind of almost like a distribution of what's happening to the limit as x goes to infinity of this 1/2 x minus 1. And then what's happening to the limit as x goes to infinity of the 3/2x plus 2. So we can split it into those two parts. And then thinking about the survival of the fastest and so on, the term that's over here, the second term, we know that this is going to go to 0 because the degree of the denominator is larger than the degree of the numerator. So that term, the end behavior, approaches 0. This term is going to approach whatever the end behavior of 1/2 x is, because that's the dominating term. And since we're on the right side, that would go to infinity. So this whole term is going to go to infinity. Kind of that reasoning of what it is, that the fractional part is so small that it tends to 0, and it's only the whole part of the polynomial that matters as x goes to plus or minus infinity. And that's how that works for polynomials. So I just thought that I would highlight that as well here at the end of the video. All right, so go ahead and try the rest of this page on your own, and then we'll wrap up this video.